应该会有啦。
你让我知道几岁的话，我命你 after 泡菜。我 I try a new if you want 啊。then we can do a time.
对哦，要那个网就没那么卡了。我在想鸡蛋，如果我的 transformer 太难了，鸡蛋那 calculation 是很夸张。
Hey, I need you all to help me to update. I think I lost the all the time. I don't know why it's not saved. Can you all help me to update this again? The group moving one.
Yeah, you yeah, you could. My group, my group.
Okay, I want to. Hey, can you help me to update this again? I think I accidentally lost the file. Can you help me to update this again? I didn't have it there. What's your name? Andrew. If you have wrote it, I would have put it into a table like this. And join one of the group can you all also put in your group? I lost it, but I don't know why you didn't say. Can you help me to put in your group again? Yep. Help me check the group Just what do you say normally? Who do you discuss with previously? Right, the last group behind. Okay. Listen to the 3D solid one. I mentioned that because of the stress contained at the top, so you have space. By right, you should have that's why I suggest you all do the pure bending case first, so that you see your what you would expect is to have a pure bending condition, your tensor and your compression. It will be really the same. Then it will be pure bending. You see what is the problem there, So that's why I started there. Because of, I can guarantee you this mask is because of some the boundary. Then okay, really, do it also the one, do the bending one can do. If the bending one will confuse you, but you should check this. But the bending one should it will be slightly off the 10%. It will be error one, and this is the machine. But I'm just saying that I will prefer to do the pure bending. The two of them should be first the bending, your positive tension correction, and because it's calculated, you keep on taking the tension stress. So you can then you know whether there's something else in the issue. If you put together the result at the same time, you can be the final reaction. Second question. Yep. If you really wanted to regulate it, then you can mention we're not saying it by right, I will explain this after I come back. That's a good point. I will explain this later. I come back. Yeah. Can you remind me this? one right. Can you help me update it? I lost it. Can you help me update it? The group one, the group six. So grouping, can you help me to check?
Yeah. But the student number still wrong.
Yeah, student number never mind.
Yeah, 对啊。Yeah, correct. Can you help me check whether your grouping is correct? I lost it, apologies. Can? Everybody okay with this? Okay, yeah? 他刚换成换掉那个11个动词，然后他又关掉那个 call。
啊，对咯。
因为我看他们的assignment是 task 跟 B，另外一个就是 shell 跟 body，因为我们的是一次过全部。我们 report 也是。
像我们的 report 就是100%的。
对对对。But then
你的设备。哦，是。干了吗？最好是没有看到。
Fourth one. Closer. Last one. So the fourth one. Sorry, third one. Anything else?
通常打灯你在那旁边。这种给人一点点不好吃，真的，外表好看，不好吃。你想吃，你试。如果是真正长相就变了，因为很早不开了。
Everybody have a group here. Anybody not in the group? Did not save it, huh? Thank you.
弄一个好笑的，谁弄一个好看的在这里弄一个好笑的。
I just want to go through something very, very quickly on the back to the assignment first.
你买给他说，给你不说吃不好吃，是可以买一鸡腿。拿一个鸡腿也那个鸡腿是一块钱。Just in time. Oh, sorry, 不是 K 还是 H？
Okay, class. I just want to say this very quickly. Okay, this is the result, right? Let's say this is the result that you have. Okay, this is the result that you have, right? You will see that there's a stress concentration here. You notice that there's a stress concentration here. There's a stress concentration here, okay? So you see, is this result make sense? No, it doesn't, because we are adding it as a point load. In reality, it will be a distributed load, but I say for simplicity, we will add it as a point load, okay? And I want to say this that, so at the first and foremost, right, that's why I wanted to put it as a bending stress here first, okay? that there's this is for the shell model, okay? And you see, just now I showed you that there's a localized, very localized code that you're meaning, right? Okay? And that's why I did it as a pure bending loop first, so that you can see that this is a pure, before you make sense of the magnitude, because the magnitude will be a little bit off, 10%, within 10% or a few percentage off, okay? But I did it as a pure bending loop first for you to, I would rationalize it this way, okay? For this need to be performed as a pure bending condition first, whereby the two compressive and tensile loop are balanced. So they show that it's a pure bending loop, which is important, okay? You might not get it's not easy to get the magnitude to be exactly the same. Sometimes it might be off for various reasons, okay? But to do it as a bending loop, that's why it's important. For your case, okay, your validation is up to you how you want to do it, okay? But if you want to do it together with axial load, like the way I showed in the example, is also fine, okay? Then you need to justify why. It could be like what I said, the rigid body motion that restraint. The thing I want to show you is here. Okay, so imagine the localized stress that we see. Okay. Imagine the localized stress that we see here. Okay, at this point. Why does it happen? It's because, like I said, it's a single point. Okay, how do you resolve it? If I was to do, does it mean that if I have a smaller mesh, I have a finer mesh, now I have 10 mesh along the width direction, correct? If I increase the number of elements, will it improve the situation? Yes or no? Why not?
Because that small point will still have.
The small point will still have the same amount of stress. That's one. If I was to, now you see, this is localized, right? So if I check the stress, right? Okay, if I replace this stress here, okay, this stress is about 12 megapascal, correct? Okay, so it's still relatively small among the entire stress, but some of you will have a very different stress. It could be, okay, this 12 megapascal. Yeah. So what will you do if your stress is too significant? I did it in the 3D model because it becomes very significant. So what you do is you just remove that section. Okay, you remove the top section. Okay. Because I'm not interested in that point. I'm not interested in that stress there. I'm interested in the bottom here. Correct? The stress at the bottom. That is artificial, really is artificial stress. Okay. But I want to illustrate to you is, if you increase the number of elements, let's say for example, let me go back to mesh. It's just not shell, right? It's not shell bending, right? Axial load together, of course, it will be higher. So you see now this is very high. Let's look just at this as okay, I want to show you. Let's say if I were to look at only the stress in this configuration. Okay, the stress here is about 56 megapascal, which is quite significant compared to overall. So you see, now this is the point, very good. So you see that now 56 megapascal is the stress at this location here. Okay. So what is the actual initial stress? Actual initial stress, we must remove the top part. Okay. So it's 54. Actually, it's 54, not 56. 56 is because of the loop at the top. And I want to show you something. Now, if I was to increase the mesh, just now is what? With the top is what? The top, the stress at the top is what? What is the stress? Is the stress? 56. Yes. Okay, 56. Okay, let's do it again. 6, right, at the top. Alright? And I say that because I don't want, I will ignore the top because that is an artificial stress. In reality, it will not be a point load. Okay, you will be 4, answer is 4. Your actual resistance stress is 4, not 6. But with the top, 6. If I increase an element, make it denser. Previously it was 2, now I think it's 1. Okay, I run it again. Okay. I don't remember, but I believe they're using the one here.
So we have to, because the one on my laptop scratches the wall of time.
Right to the body.
There only no one.
I go to my mobile.
I think they-
Oh, Joshua. Wait, before that. Let's take a look at it. Just now is what? Remember the stress? You see,
56.
56. Now what is the stress here?
11. 140.
Alright, it's 114 now. Let's zoom in now. Stress at the top is what? 114. So what? The stress increased by how much?
Double.
Twice. Why? Because originally, right, when I told you it's artificial load, okay, you input a point load, there's nothing wrong with that. In practice, that's what happened, okay? But I will remove it because in reality, nothing is applied as a point load. It's infinitely small, as a very fine point. No matter how much stress load you apply, there's always a contact surface, alright? So that load will be distributed across the contact surface, but now you're assuming it as a point load, which is 0.001 So that is 56. When I increase this density here to something even finer, okay, smaller, but this is n equals to 2, this is n equals to 1. The global seed size is millimeter, okay. So what happened is that means you're trying to calculate what this load will be handled by one element 2 by 2. This load will be handled by abacus 1 by 1. So of course the contact surface shrink by half. The error in the concept, this is called localized stress. The localized stress will be even higher. Okay? When you see something like this, do not just blindly give the result here. Okay? Then you know what I mean? So that's why using a very, very, very refined mesh is not wrong, just that you need to understand that there's certain thing you need to filter out, which is this localized stress here. Okay? Do you understand what I mean?
So this one you compare the mesh also.
No, that's why you compare the mesh using the deflection.
Can you use this as well?
You can't use this localized stress to compare it because this stress you need to take it out. Yeah.
So
But you
yeah.
know what I'm trying to say?
Yeah.
Okay? So this is the stress. That's why when you come out with the figure, right, suddenly the maximum result will jump. And it could be due to this localized stress. And I'm trying to illustrate to you most of the time your error is because you have not sufficient mesh density. Okay, it's not sufficiently fine. Just now we say 2 element across thickness is not good. Okay, but then if you have it too fine, you could have things like this, which is okay. We just need to remove the top layer. Okay, if you see if I was to remove the top, right, the result is exactly the same as what we had just now for the 2 by 2, 54. Okay. So this, the 54, which is the bending stress at the bottom, is correct. Okay?
But removing the distance will get affected.
I can't hear
The
you.
distance will get affected.
I can't hear. Somebody is talking right beside you, that's why I can't hear. Yeah.
By removing the distance will get affected. That's the point that you said.
No, only the stress. Yeah. Okay, no, it does, you're right, it does affect because that just now the question, do you all hear the question?
Yes.
You all need him to repeat again?
Yes.
Yeah. By removing the top layer, deflection get affected.
Yes, it does get affected. Because your top will see the highest deflection, right? So that's why that's a very good point. So when it comes to the deflection, you shouldn't remove the top element. Okay, you should remove the only for the stress. Okay, that's a good point. So let's put it back again. Let me
Like
finish
very
first.
clear.
Yeah, wait, let me finish first. So you see, if I go back to the displacement, right, you see the displacement doesn't see a concentration. Only the stress see the concentration. You see that? The displacement doesn't see the concentration. You only remove it if there is a stress concentration. Right, you see that? Now the displacement doesn't see anything. Okay? But if you go back to the stress, you see go back to the stress, you see the concentration there. Right? So it's only for stress concentration.
The model is
You better say something.
No, the model is same.
Yeah.
So if I tell it, it is going to affect the whole model.
No, that just now
That's only for
just now that removal, right, is only for it doesn't, it's only for display only. So the model is still the same
It's
model.
still the same.
It's just like I want to zoom in to focus like what I did.
So if I give the next time I just can open the report and become a normal one.
Correct,
So this-
correct. Everybody understand that? Can That's a good point. Okay. So what I'm going to do now is I'm done with assignment 2. I want to go through very quickly the entire this module and a flavor of what to expect in your exam. Yeah. So what you're going to have right in the exam is you are going to have 3 sections. Okay, one is on the calculation, one is on the. Can you everybody which one? Everybody can write it down. Okay, everybody write it down. And one is on the calculation, which is your direct statement method, and is another one is on the beam and truss, another one is on the plate and shaft. Plate and shaft.
Compression method, beam and truss.
Okay, I repeat, it's not plate and shaft, so it's shell and your 2D solid, shell and 2D solid, sorry, shell and 2D solid. So first is your direct stiffness, second one is your beam and truss, third one is your shell and your 2D solid. Okay? So it could be 4, it could be previously is in the previous exam it used to be like used to be 4 questions. Okay, so the first 2 is on the calculation, the other 2 is on the beam and truss and this shell and solid. Okay, but I wanted to say is so spend your time wisely. Okay, the calculation one definitely you have the lowest mark. You look at your assignment, you know already. Your assignment one is only 10%. Okay, so the direct statement method is going to definitely be the lowest mark application. Do not spend the time all of the calculation. Okay, just use the time apportionately. Okay, you write something, I can give you mark. If you leave a blank there for me, I can't give you anything. You understand? Hello. You know or not? Okay, so make sure every question, don't care, just make sure you have something there. Understand? Okay? Don't want anything for 0, no. Can you show the pass? No. Good question, but no.
Is there a date for the exam?
I can't hear.
Is there a date for the exam?
Huh?
That's not big.
No, I told you. But there's no exam, right?
Yeah, it should be the 3rd week of April. About that.
No, I mean, start with
It should be the Saturday lah, same lah. Normally it's Saturday lah.
Saturday. It cannot be 30 or 30, but start from the start. Oh.
So what I'm going to do now to help you, normally that's what I do. I will draw certain geometry and I want you to do the same thing. Okay? Draw and include it the few things to make it a free body diagram. Then also tell me whether is it a beam model or a truss model. Okay? Okay? Okay, this is like a bit like your, this is, you all doing here is your own pasar area, up to your one. Voluntary to stay back now, up to your, okay, you all can go now if you want to. Okay, this is like a flag, like a banner pole that I have, okay, there's a banner across, it's subject to the wind load, okay, I'm supposed to analyze what is the stress applied on this load here. Okay, this is the first configuration. The second configuration is okay, this is a bit like your no, this is your like your basketball frame, okay, whereby they have a basketball, then you have a load here, okay. So I will have two volunteers to write. Okay, I want everybody to draw this, and I want you to write what do you think. What is this? I need you to come up with, okay, what I'm trying to do here. So the exam will give you a problem like this, and you're supposed to create a model. So of course, to create a model, you need to know what is your free body diagram, right? Okay, so I want you to draw your free body diagram, and also what is the element, what is the number of element, what is the model, what is the number of element you need in each member, things like this. So I'm trying to help you to create the model first, and you can easily do this in Abacus, correct? But you all know what I'm trying to say, what I'm trying to do here, okay? Go through the motion to think what you want to create in the Abacus model, okay? So I want you to know, number one, what is the free body diagram? Number two, what's the type of model? Okay, number three, element number. Okay, manually mesh up like how many elements you wanted over here. Okay, draw these two.
这一定是冰，是冰，这个是 cross。
That's why I say the most important thing, right, is to draw the diagram already. Then when you have this done already, when you create the model, it's going to be very fast. Oh, sorry, I forget. The other one is the boundary condition. Oh, yeah, it's here already. It's your free body diagram here. Okay, look.
But the load
Yeah,
direction.
the free body diagram include load, right?
Yeah, but the load
Oh,
is.
the load. Yes, good point. Sorry, I forgot my point. Okay, the load is in this direction. Okay, it's a wind load. Correct? This is a wind load. This is a post. I have a banner here. It's actually the wind load.
X direction.
Yeah. So it's
Z.
in your Z direction, correct? X, this is the Y, Z point. Okay, this is the downward direction. Okay, so this is the X, Y. Okay, the load will be in this direction. Okay? Y, Y. Okay? Can. I give you 10 minutes. Let's do 10 minutes. Take it through in the exam condition. Okay? Feel free to discuss if necessary. But the whole point is I want you to think critically because that's what happens in the exam.
Can discuss.
Of course.
Exam and
I mean now is I want you to have a flavor. What I'm trying to do is have a flavor of what you're going to be tested on. So you don't need to discuss go ahead. With what I'm trying to let you do right, you will be able to help you quickly create the border. Okay? Yep. Oh yeah, wait, sorry. I think I make it revise. Okay, revise as this.
Yeah.
果是讲 element size 的话，是 dependent on 它的 scale，就是你要懂它的 number one 这个 display。sorry, the element number is not element size, right?
That means number of elements in each element.
Oh,
So you cut it, like
oh,
cut it like
oh, 就是 one。没有 one 是 for maybe for 这个啦，这个 maybe 讲 ten。
Okay, this one is a hoist. It's those hoist crane that you see. Okay, so it's like a cantilever pole. Okay, and you have a lateral brace with a hinge on each side. Okay, so what is same thing? What is the free body diagram, type of model, element number? Okay. Hey, can you draw? Take a piece of paper and draw. Everybody take out a paper and draw. Okay, try this one. You try this one. Try question 2.
Sorry, all these are point load, right?
Correct. All point load.
So the wind only blow the downside of the pole lah, not the
Oh, okay. Sorry, my fault.
Or maybe someone push the beam just at that spot.
In this case, because it's in this case because it's a banner, right? So I'm artificially thinking of the way, right? Okay. So it will be
The whole area.
tied to the top and bottom. Okay. This there's a fact that it high to the top of the camera lah, yeah. Okay. But it's a good point. Okay, it's a good point. Okay, since you asked, you do the first one. Go.
So we assume two points of load.
Huh?
We assume 2 points of load or 1 point.
You just do first, then we can talk around the way. Do the second one. Okay. Now, so when I say the type of model, class. When I say the type of model, right, I mean that in this case, Is this a beam or truss model, or is it a shell or 2D solid model in this case? Huh? This is a what? Huh? Who think that this is a beam or truss model? Who think this is a plane? That this is a shell? Who think that this is a shell or 2D solid model? Shell or 2D solid model? Huh? Who think it's a beam and shell? Sorry, who thinks a beam or truss model? Put a hand, straight. Okay. Who thinks it's a shell or 2D solid model? Straight. Okay. How are you going to do a shell model in this case? Yeah, it wouldn't be a shell model because all this is a 1D element. All this is a 1D member. Correct? Do you see what I mean? All this is a 1D model. A shell model or 2D solid model, you will see a plate or a shell type of model. Correct? Okay? So this must be a 1D beam or truss model. And when I say the type of model, I'm asking you whether this is a truss model or is it a beam model. Okay?
So the P not important.
No, it is important. Okay? The other thing is, remember when we create the model, when you create your part, why? No. You frown, I want to know what you all have any question on, because this is exactly the question you're going to have. When you see the question, then you ask yourself, is this in a 2D space or 3D space? Huh? Who say it's 2D? Put out your hand. Who say it's 3D? Put out your hand. One more time, who say it's 2D? Put your hand straight, put out straight. Hurry up. Hey, hurry up. 2D. Straight, put it up straight. Commit to it. Who think it's a 3D? Put out your hand. Okay? This must be in a 3D space. Because in the 2D space, right, you only have your X and Y. But in this case, the load is in the Z direction. Alright? So it must be a 3D space. Correct? Louder, I can't hear you. Louder. Then you ask them to.
So my understanding is truss and beam model is in 2D space. So it can be done in 3D.
Correct. When you create your part, right, you go to beam model, correct? Then you ask you 2D space or 3D space, correct? Okay, then the third one, when I ask element number, alright, I want you to manually discretize it. Manually cut it like number of elements within each member. So you will draw it up how many member you want.
Within each member.
Yes, all the member. So I want you to manually draw it for illustration's sake, whether you're going to have one member or you're going to have it as 10 member. Okay? You can just make a note there, you can just make a note there.
You mean the node?
No, the element, I want you to subdivide it so that but it's as good as you are manually doing the mesh module here. Okay, because this is where a lot of problem comes in. Later you will see what I mean. Okay? It's one member, but he said one member. But I know where is the problem, but this is exactly what I understood. When you have a problem like this, then you need to start thinking. Is it a shell? Is it a beam model? Is it a shell model? Is it 2D model? Is it a 2D space? Is it a 3D space? How many elements? What is the volume? What's the number? Hey, who draw this? Can you rewrite just now whatever you understand further? Go. I need somebody to do question 3. Who want to do question 3? Hey class, you don't understand why I'm coming from. You need this before you create a model. Correct or not? The very first thing when you create a part, beam model or shell model, correct? 2D space, 3D space. This is all the thoughts you need to go through before you actually create it. Right? Huh? No, it's not.
This is what?
Just like I said, this is the hoist, and you have a lateral brace, which is a pin joint, a hinge joint. Okay, this is a hinge joint. This is a hinge joint. This is for the truss, you know. But the other one is still continuous here. Hey, you all need to start writing. Can you, everybody, based on what you understand, work on it, work on the 3 problem. This is going to be helpful. I want this to be helpful for you all. Do like what you are doing now. Okay, do for all the 3 problems. I want to see you draw the same thing as what you are doing now. Right. Think about it. Do you all understand what I meant? Yes? Right. Ask yourself this. How many elements per member? You all get it? This one, ask yourself, is it a beam or truss model? Is it 2D space or 3D space? How many elements per member? Right. Hey, you all want me to go to one by one, then you all will write. You say, wow, yeah. Hey, I want to see everybody write something down. If not, we're not going to go through. It's not going to be right. Just write something first, then draw the border condition. Yeah. Then this one, talk about this one. Done? Can, go. No, what is the space? Give me space. Right now. Boundary condition now. Okay. So how many elements divided like this? Per member. So we have one element here. One member here, one member here. So you just subtract. But it's one and you Hey, you all three don't go back first, huh? Don't go back. You all get it? Hey class, you all get it? I want to see everybody right now. You need to go through that thinking process. Okay? Remember what I say, first one. Is it a B model or class model? Is it a 2D space or 3D space? I want to see everybody write it down. Then for each member, how many elements you expect to see there? Then draw in your boundary condition for each of these three questions. It takes the opportunity, right, to go through this. In the exam, you will be confused. So take the opportunity to write it down. Go through that thinking process. No, three of them go back. You all must explain later.
anyhow do.
Can pass.
You know what I say? Is it a beam or trust model? Which one? Are you all done?
Yeah, we're done.
Are you all done? Done, huh? Okay, let's go one by one, huh? Who is going to be first? Question one first, huh? What?
No, it's just my record.
So do you still need it? Don't need, huh? You wait away, huh? This one don't need, huh? Can you draw so that they can take reference on it? We still need to do the shell and do this audit, okay? So we will allocate 30 minutes each. So I will go through this quickly, let them give them a chance to explain. But then here, you don't. This is one. Okay, well, let's go to question 2 first. Yeah, same thing you ask yourself. What is the question you ask? Whether is it a beam or truss model?
Plus, because of the racing.
Hey, do you all want to listen to this? Okay. Why is it a beam or truss model?
Trust.
Truss. Why truss?
Because of the bracing.
Yeah, because of the diagonal brace. You see that it's stable, alright? Even if you put it as a truss, it's stable. Of course, it's arguable, you can put it as a beam, correct? But for exam condition, if this is obviously a truss, you put it as a beam, you'll be penalized. You will not be totally wrong, but you'll be penalized, of course. Remember what I said? If it can be done in a 2D model, will you do it in a 3D? Okay, but if you do it in 3D, is it wrong? It's not wrong, just that you'll be penalized because you could do it in a simpler form. That is the whole point of finite element, correct? So likewise, if it can be done in a truss model, it ought to be done in a truss model, correct? Okay, because there's a diagonal brace and it's still stable. Continue. Then is it a 2D space or 3D space?
2D.
Why?
X and Y, because the load is only on the Y axis.
Okay.
2D space, and so for truss only one element each.
Wait. Then you must go and explain the boundary condition.
All the boundary conditions are on both sides, and on the Y axis and also on the X axis.
Yeah. So in this case, the boundary condition, let's say if you're thinking of, let's say it's a basketball frame, right? So by right, here will also be restrained, okay? You will only have a roller condition, let's say in a bridge, where you physically see a roller there. You know, only certain things allow for expansion joint. You must have seen this expansion joint before, correct? You do see a roller at the end where it's allowed to expand. But in a basketball court condition, you know it's going to be anchored to the ground. So it will be fixed in both the X and Y direction. Correct? Okay, so this is the early part. Last one, number of element.
One each. For
Why?
Truss. Truss is only one because there is no bending.
Yeah, you all hear that? For truss model, each of these is one member. Alright? Each member for truss model, how many elements must you have? Huh? How many? How many? One. Okay, so this is correct. Thank you. So for I will want to check already, then you will still ask questions.
Do we still need to put the boundary condition for here or just one point?
Both.
So need to do both.
So good. Can you say louder?
So for Abacus, when we do the modeling, do we need to put a boundary condition for both ends or just one?
For both ends, like for both points,
Yeah.
right?
Yeah.
You need to put both. Of course, you need to put both. Okay. If you don't put both, then this part will slide out. Remember? It will move. Right? It will move. So must you do both? Yes, you must. If you think about it, because you are restraining both conditions, right? By right, you do not need this member. By right.
Oh, okay. Both conditions.
Because both point is being restrained, right? You do not need the bottom member by right. Agree? Because it will not have any stress at all. Yeah. There's no displacement.
So that's assuming the member is basically at the floor, right? If it's slightly above, then it's still considered.
Yes.
As a bit of stress, right?
But then, you're right. But then now you are drawing exactly at the bottom, you know. So if you restrain here, then you will have deformation at the bottom, okay. But it's a good point, but you wouldn't, you really wouldn't see any deformation at the bottom. Thank you. Hey, clap, eh?
So it's a 3D beam.
Hey, one by one, yeah.
Yeah.
So first thing is, it's a beam model or truss model.
It's a beam model.
Why?
It's because this one, if it's a truss model, then this one will fail. And you collapse, no bracing. So only can do as.
So in this case, right, it must be a beam model, correct? Because this is like a cantilever post. This is like a porter frame. Each member is like a prop cantilever, correct? In order for this to be a truss, you need a diagonal brace in the middle, likewise throughout the entire cross, correct?
Yes.
So is this a 2D space or 3D space?
This is a 3D space because this one have Z direction. So
Yeah. And you will expect the deformation to be in
the
the
Z direction and also the Y direction. The X.
yeah, you expect it to have, it is free to displace in the both X and Y, including the Z direction, because your load is in the Z direction. Okay? And you will expect, if you are right now, actually you will expect it to be in X direction also, because as you move in, imagine this is move in, right? So this thing might walk in this direction, correct? This post will walk like this as you move in this direction, correct? Okay, so it will be free to move in all three directions, unlike 2, correct? Unlike question 2, but you only see a downward load, correct? You all see that? You all don't understand your math sliding rule, right? If the exam, how are you going to answer this? If you can't even do this, how are you going to create the model? You know what I'm trying to say. That's why I want you all to go through the thinking process at this point in time. Can? Continue.
Then the force is coming this way, so I pinpoint two loads.
Yep.
Then instead of the whole area, this point meters up, so we point to the. Then boundary condition will be placed at the bottom. You'll be restraining everything. So rotation and also rotation in every axis and also XYZ axis.
Do you all hear that? You need to restrain the rotational degree of freedom, correct? Because it's a cantilever downward, so you must restrain it rotationally, correct? All three directions. Make sense?
Yeah. Then lastly, the element of the 10 per element.
10 per element. Actually, what I wanted you all to, by right, what I want you all to draw is to show this. Even this is everybody will remember to do it most of the time, but you must also do the 10 element here. You know why? Because in your global seat, you only assign one number. So sometimes you only remember to do this. But here,
the total length, then we know how much to assign. Like, for example, if this is like 1 meter, then you put 0.1 meters.
yeah. Do you hear that? If this is 1 meter, how many do you put?
0.1.
0.1. If you put 0.1 here, we only have one element.
Or 0.0.
Do you know what I'm trying to say? Actually, you don't need to think about this so much. It's when you mesh it already, then you see the number of elements here, then you will know.
The smallest area.
Yeah, the smallest member. That's why normally if you, I never show this, but if you can go into the individual edge, the individual seat, you don't do it as a global seat, you can do it as an individual seat also. But it doesn't make sense if this is only one member, one element. Okay, this must be at least 5, 6. I don't need it to be strictly 10. Nobody going to tell you it's going to be strictly 10, depends on condition. But it can't be 1 or 2 for sure. You know what I mean? So that's why this is exactly the problem. This is 1 meter. Your global seat cannot be 0.1 because here will become 1 element.
So I would say like this one is, this whole thing is 10, this one is 5.
Yeah.
So we do local seat.
You can do a local seat, correct. Okay? And it's going to be very fast in any way for a beam model. So it doesn't really matter. Good job. Thank you. Do you all understand the first 2 questions? Okay, let's do the third one.
So my boundary conditions is also
Wait, set. Is it a beam or truss model?
It's a truss and beam model.
Which one is the beam, which one is the truss?
This will be the beams and the truss.
Do you all see that? Because it has a bending, so the post and the beam must be a beam member, whereby it's allowed to deform, okay, with a curvature. Then
This
the
is
diagonal,
a 2D model.
yeah, the diagonal brace will be a truss model, correct? Because it's a hinge at both ends, correct? Then it will be a
2D.
why is it 2D?
Because this is supposed to be a Y.
Yeah.
So it's only Y and X. Yeah.
So you only have a deflection force in the y direction, right? So you only expect the xy direction deformation, correct?
Yeah.
Then the boundary condition.
The boundary conditions will only be upper and bottom.
Yeah, but okay, so other than this and this, right, you also need to restrain rotationally. Alright? Okay? Then what about the number element?
Because of the truss here, we have to segregate into different parts. So this side is then one for the truss.
Yes. You all get that? You all get that? Can? Okay, thank you. Sorry? If you do everything as a beam, right, is there anything wrong? Class, do you all hear that? That means you're saying, say, here, you can put it as a beam, is there anything wrong? You will get the same result, but the same thing wrong.
It's just that
Because it's hinged at both ends, right? It will be as a truss. Okay? Because it would does have movement, so it's not going to, it's only going to see an elongation of compression. So actually it will have the same result as truss. But you could have done it with truss. And then the truss member is so No, only that one member will be a truss. The rest will be a beam. Do you all get that? Huh? Hey, class, do you all get that? Okay? No. You can do it all in one model. So it could be a beam model. You draw the whole thing, correct? Then this member, then it be a truss member. Okay, then the other two can be a beam member. You can try it at home. If using abacus, you find that in your model, right, you can assign both as either a beam or a truss. It's okay. Okay?
So this is one part.
Correct, it's one part, only one part. You just assign in the property module, assign that as a truss. Assign the diagonal brace as a truss. These two, the post and the beam as a beam element, as a beam model, as a beam section. Okay, the diagonal brace as a truss section. Then when you come to the mesh module, likewise, this as a truss element, this as the beam element. Okay? Are you all benefiting from this? Yes. Okay? Remember, in the exam, you're only given the raw conditions, the original question, and you must think of all these things, how to do all these things. Okay? I can't hear you. I will go through, I'm going backwards now, so I'm doing the beam and truss, shell, do this only followed by the direction that you have.
So the dimensions will be given for the
Yep.
the
Yep. For sure. Good point, but for sure. Try this one.
哪个第一个？第一个应该是手语，第二个是手。Yeah.
the first one is it a plate at bottom side or
Or it's just a flick. It's
so
just
it's just a U and
yeah. It's like a flick. Yeah, correct. It's like a N. It's like a N shape.
Oh.
What is it? Inverse U. It's an inverse U. You mean that? Hey, I don't get it. You must tell me lah.
Okay.
What?
I thought the plate was just a illustration, but okay. So it's part of the whole.
Yeah, these are like sitting on a pin kind of thing like that. Okay, so I'm only interested in the reflection. This is like a bridge. I have a point load in the middle. This is like a disc, and half of it is subjected to a compressive force. Okay. Can we do the same thing? And we have two more. Do the volume here. But you also find it right. I don't want to repeat the same thing, so I want to know whether you understand what I'm trying to say. Obviously, this is going to be a shell, plane stress, plane strain question. Okay? Let's do it this way also. Not straight enough for you, is it? Huh? Is it? Who is confident you all can come up and write, huh? Ask the same question I asked you just now. What is the same three questions I asked you? Anybody want to volunteer? Anybody? Have you all done it already?
我应该这应该是区域手艺，
这是区域。
这个是独立小，独立小这里可以这样，但是这样子没有这样。这就可以，但是这边要有水，在这边是那个应该是这个，我不懂。
可以对不对？
嗯？
对，因为在那边出了一个通过了，出在那个可能。
他抓具体东西可以是你训练的，可以是抓很多的。对，然后他可以画一个。中间的话应该是全部啦。
Hey, can I do volunteer?
上面应该有啊，
下面应该
只是一个外的学生。
unless 你不要它动的话，就 X 来就出来。
这样子，我这样子的学生，这个是 C 的 rotation 的网页 ，C 的 rotation 里面，然后就根本就不动。
也是啊，全应该是，assuming 他讲是地上，所以 assuming 他不在地上的话，就是上面那个人 just 抓出来，这样按的话呢就不需要有血了，可以这样。把新车有画地板的话，这个应该要人讲他没有，应该 rolling 没有，因为他自己考得自己。把它考得，如果你东西没有动的话，就没有效。所以 assuming 全部是 continuous 的，人这边推这边推应该跟着，所以你这里不需要学，因为它没有学。But 中
这个洞是要圆吗？
呀，应该是呀，restrain 啊，可是应该没有 restrain，没有 restrain。
其实这边是根本没有光那个东西吗？
呀，应该没有，应该没有。
把它的 animal 放在附近。
可以，go。
呀，因为削的话，你做圆的话，就是你不用restrain，只是因为削的话，这样只是你要 assign thickness，所以所以你只是画一个circle，然后 assign 个 thickness，中间应该没有。这个我不知道。呀，应该是这样，应该是一个。element 的话 maybe 因为削的话应该是 element 应该是1。
原来是 the first one。
因为削的话，它是一个线，它有些就是一个线。
I want you to do on top of that, right? Just like how we discretize this, right? I want you to draw a mesh. Do a quick one. Okay, just rough idea. Okay.
就是。
那小是外面试一下，两个是过一下，这里可能就在这边会是有10到20。
对，不管是讲削没有，我没有看得到，因为这种削没是因为我们会有修这个，我们会有新的，我们也是有新的，不是没有底的，只是要看它 stress 多少而已，所以应该是我，我比例吧，比例是吧。
Hey guys, see this one right, I want you to do it how you would want to discretize it. So is it when you mesh it, are you supposed to see it this way? How are you going to see it? Do it. This is important. I have a point to show you later. Okay?
如果这样的话就变成sorry了，是选。
啊？
这样子的话，就是立场。因为我觉得这样子是不有的，所以他决定不用去看那个，不用去看这个。我不知道。
That was what I wanted to see. Right. Then what about your other than that, what else you doing? Yep. And your body condition, right? Your DM, your frequently your F, BF.
Yeah.
NFC. Your freedom and your body, so your body condition is assured. Okay, then you can draw the mesh. When you mesh it, what will it look like? Just bear with me for another 10 minutes, is it okay? We're supposed to end it today, right? We're supposed to end 6 today. Correct? Not 5:30, right?
这个是 plane stress。
Do you all see why I want you all to draw in the mesh? You all see why? Okay, so you know where to pay attention. Okay, and you will watch out for certain place. You know, like what I say here. Okay, it's not that just these have enough element. No, here need to have enough element. Each member also. Correct. That's why I want you to draw it out. Then you have an idea. Then you have a better appreciation. Why? What is where I should observe in terms of the mesh density at certain location. Okay, are you all done? Huh? Okay, wait, what are you doing? Okay, explain. This one first, this one first.
This one first.
So this is a this, remember we said this is a this, a circular this. Of course, both model in this case based on the geometry is thin. In the actual exam, they will give you a geometry, but you know it's going to be thin, for example. Let's give an example. Let's say, for example, this is a 20. This is a 100 millimeter. This is a 100 millimeter. This, okay, 10 millimeter thickness. Okay, this is, let's say, for example, 50 meter length. This is like 2 meter. Okay, this is about 20 meter. This is about 30 meter. Okay, let's say for example. Okay, it will give you something like this, and you can appreciate. But based on the geometry, you can roughly describe. Come, let's start with this one first.
Okay, so what's that?
First thing we ask ourselves, correct? Is this a shell or is it a 2D solid model?
This one is a shell.
It should be a shell, but can it be a plane stress or a plane strain model?
Plane stress, yes.
Why plane stress model?
Because the force is acting on the surface.
Okay, because the force acting on the surface. Other than that, it's a very thin model, correct? We say this is a 2D space or 3D space? Huh? It's okay, it's okay.
2D.
Huh? Why 2D space? Who thinks it's a 2D space? Put up your hand. Who thinks it's a 3D space? Put up your hand. Who thinks it's a 3D space? Put up your hand. Who thinks it's a 2D space? Put up your hand. Who never put up your hand? No, serious. I want you all to understand. I want you all to, if you're not clear, you need to think about it. If you're not clear, it's fine. Okay? Got to be 2D or 3D space? A class, 2D or 3D? 2D. Why? Because I am only applying the load, okay, in the X and Y direction. So do I expect any degree of freedom in the Z direction? No. Correct? So it will be a 2D space. If it's going to be a 2D space, I know that it could be a shell or it could be a plane stress element, correct? It could be a shell or it could be a plane stress because it's thin, correct? So it could either be the shell. If it's going to be a thick element, can it be a shell? Preferably not, okay? But because it's a thin element, it could be a shell or it could be a plane stress condition. But because it's in a 2D space, I can do it a plane stress. If it's a 3D space, can I do a plane stress? Cannot, correct? So because it's a 2D space and it's a thin element, it could be a plane stress element. It could be a plane stress model, correct? Okay? Then go on, the degree of the boundary condition.
Condition here.
At the bottom, okay, at the bottom point, it will be the boundary condition. The boundary condition is in what direction?
What's that?
Put it in ux, uy. Can you write in ux, uy and whether there's any rotational degree of freedom? Put ux, uy. Then does it have rotational degree of freedom? Who think that you need a rotational degree of freedom? Put a hand. Who think that you do not need? Okay, actually you probably do not need that because there's no rotation per se. So but you definitely need an X and Y direction. Okay, but because it's a single point, okay, I probably will add it because it might not be stable. I just bring this to thought. Okay, if you really do it right, it could come a place that it's not stable. Imagine if in a space, right, the whole thing is anchored. If you have a structure and you only have one point, uy and ux, do you need to ration it rotationally or not? You probably need, because any type of disturbance could cause it to be unstable. If you put it in, it's not going to change the result. Okay, I will probably put it in because it's a single point restraint. Okay, do you all get what I mean? Okay, so can you put it in the rotational also? But you all know because it's a single point, correct? If it's distributed, let's say for example, we go to the next one. Put it as RZ. Okay? Thank you. So it will be U, X, U, Y, and your R, Z. Make sense? And like what you can draw, you have tried to make it as 10 elements through the width itself. Then it makes sense, correct? If you only have 2 or 3, then it's not enough mesh. This is probably, it looks right to me. Okay? Got it? Okay? Next one. For this. So this is going to be a 2D space or 3D space. And can you answer like what I will ask you? You answer so I know that we all understand. Come.
3D space.
Why is it going to be a 3D space?
Because I think from the Y and the Z vector.
I keep asking the same thing, you just continue. Then, other than in the 2D 3D space, what's the next question I will ask?
Is it shell or
Good. Is it shell or the 2D solid?
the shell?
Why? Who thinks that this is going to be a shell model? Put your hand. Who thinks that this is going to be a 3D solid? 3D solid. Okay? Who thinks that it's going to be a 2D solid? Okay, good. So it's most of you think, one more time, who thinks it's going to be a shell? Put your hand. Who thinks it's going to be a 3D solid? Okay, why?
Depth.
Huh?
Different in depth.
Different in depth.
Yeah.
But why different in depth? There's no different in depth.
I mean the plate, the bottom.
Oh, my fault. Okay, only the two plane you're not considering the plane.
Oh, you're not considering.
Only the inverse end. Only the end we're considering.
Then 2D.
Huh?
Then for 3D plate.
I give you one more time. 1 minute to think about it again. Think carefully. Only the one he mesh is important. The two is just, and you exam you will see this. You will see the two pling there, don't do mesh the pling, don't do more than because there's no dimension. You cannot mesh also. You cannot draw anything also. There's no dimension. Okay. So one more time. Think carefully. I ask again. Who think that this is a 3D solid model? Who think that this is a shell model? Put your hand. Who think that this is a 2D solid model? Okay? One more time. Who think that this is a 3D solid model? Who think that this is a shell model? Who think that this is a 2D solid model? Number one, in a 2D solid model, it must be in the XY plane. Because remember at the beginning of the lesson I was sharing, you cannot have a degree of freedom in the Z direction. Correct? So if it is in the 3D space, for sure it cannot be in the 2D solid. Okay? Everybody got that? Number two, is it a 3D solid or is it a shell model? Shell. Why shell? Why shell? Why shell? Huh? I can't hear you.
Because of the material.
So it means what? It must be thick or it must be thin? Thick to be what? It should be thick in order for it to be a 3D solid model. Okay? If it's thin, you're assuming a linear stress across the thickness. Actually, that means that the thickness doesn't make a difference. If it's a 3D solid, let's say like a block, okay, like a block. This, let's say, imagine this is imagine like something like this, okay, something like this. This geometry, the thickness is not insignificant. The thickness is important. So you need to model this as a 3D solid to be something like this, okay, by right lah, okay. But let's say something is very thin, okay, something like this, something very thin in the thin direction, then you can model it as a shell model because the stress distribution through the thickness is not important, okay. So this, because it's relatively thin, it ought to be a shell model.
How do we determine which is thin? Because that's a 2 meter, right?
Yep.
So
Nobody is going to give you, people academically, people are going to give you something, but then in actual practice, it differ case to case. But maybe 1:10 or 1:5, maybe about there, 1:10, 1:5, 1:5, 1:10, that type of figure is good enough. Relatively thin. Okay, let me ask you, you try to think about it. Is this a thin condition or a thick condition? Thin, okay? Is this a thin or a thick condition? So nobody can give you an answer. It depends on the condition you're subject to, but maybe 1:10, 1:5, about there. Not a good answer, right? I know. You know why it's not a good answer? You know why this is not a good answer? Because in reality, as a finite element engineer, I will do one case as a shell model, and I will always do a 3D solid to show that actually the shell is good enough. But if I do it as a shell, it makes it very much faster. I see the stress distribution through the thickness not significant. I will do it very quickly. Okay? Okay? Can? You see that now, there is I wanted to highlight one more thing, because it's a shell in the 3D space, right? You will see a stress difference in the thickness direction. Remember? Do you think that you see a stress difference? That means outer fiber and inner fiber. You will see a stress difference, right? Because now the outer fiber and inner fiber, you will see that bending stress, the compression and tension. Okay? That means there is a stress variation through the thickness. But because it's thin, it will be linear. So it could be shell. It will be linear. Okay? Unless something thick, let's say I have something like this, a block like this. If I bend it, I cannot assume that the stress will be linear. You probably need to do it as a solid. You know what I mean? Okay? You all understand that? Can
So this one is?
So this is probably a shell because it's thin. Okay? Can it be a 2D solid? Can it be a 2D solid? Huh? Can it be, who says it can be a 2D solid? Hey class, why it cannot be a 2D solid?
This one's got the Z direction.
Louder.
Got Z direction force.
So if it's got the Z direction for, can it be a 2D solid?
Can I put like
Can you say more confidently or not? It cannot be a 2D solid because you have a Z force, okay? You have a degree of freedom in Z direction, so confirm it cannot be a 2D solid. Alright? The only, huh? It's in the recording, go and listen to the recording. Okay? So the difference is only whether it's going to be a 3D solid or is it going to be a shell model. If it's a thin model in the 3D space, it can be a shell. Okay? So can you continue? In this case, what is the boundary condition?
X, U, Y, and Z for both sides. So you will not rotate.
Yep. So you see, just now remember I was saying, if it's a single point, you need the rotation. Because if there's inequilibrium at both ends, okay, the whole thing could just rotate. That's why you need to have that rotational degree of freedom at least this. Alright? Okay, just any small difference, if it's a single point, could cause this thing to be unstable if you only have a single point restraint. But in this case, because it is a restraint across the entire length, you need to restrain rotationally only because the restraint itself will be the equivalent couple. Alright? In the RZ direction. Correct? Yes? Okay? What else? So it will restrict only in the UXYUZ across the entire width here. Okay, so everyone will be restricted throughout the width. Okay, and the number of elements. If it's 3 elements, who think that this is enough? Put a hand. Who think you need more mesh? Everybody just say, oh, I need more mesh, correct? So, how many you probably will put? Maybe about 5. 3 is probably too little. You definitely will see such a thing. So imagine how is this going to bend? Imagine how this is going to bend. You will see the stress difference across this width. You have only 3 number to represent the curvature in this direction. Is it enough? No. Right? You probably need about 5 because you're bending. Imagine this as a cantilever beam. Okay? Is 3 enough? No. You probably need about 5, right?
手力才会，它手力才会把这个变成一个。
然后可以带进来。
Alright?
双的话会是这样，反的是不一。
Yep. Okay, that's all for the shell and the 2D solid and the 3D solid. Okay?
The left is staying from
Sorry?
is there anything straight?
Plane strain. Plane strain is, let's say for example you have a cantilever, you have a prop cantilever, or you have a embankment, like a prop cantilever, that thickness is infinitely long or a dam kind of thing, yeah. Then you will have normally mechanical structure, you very hard to have, unless you have a gate, or you have a wall, that type of thing, very long width one thing. You want to model the cross section, then you will be a plane strain. Okay? Can? You don't want me to go through very quickly on the first question? Yes?
Yes.
I do not want to call everybody back, so if you think that it's you want me to go off, please go off. I'm fine with it.